All right, everybody, we're going to expand our knowledge of Lewis structures towards that story I was telling last night about the relevance of Lewis structures and how they can predict things like polarity if we do them properly. So here we go. We're going to draw a Lewis structure for these two species. One's an ion. It's the triiodofluoroborate ion, of course. What? No, don't worry about that. Everything's got a name. And this one is trifluoroethylene, if you're curious, but don't worry about that. That's organic because it's got a C bonded to H. This one's not organic. We better do valence electrons for the non-organic one. VE. How many electrons does fluorine bring to the game? 7. Boron, 3. Each iodine, 7, and there's 3 of them, and an extra electron for an anion. So 28, 29, 32. Yeah, 4 times 7 is 28, and then 4 is 32. You get 4 sevens there, don't I? And yeah, central atom, not generally F, is it? No, F likes bonding once, so it's usually around the outside. Same for iodine. B's in the middle. So we're going to put B boldly in the middle. On one side, we're going to stick the F. And I know boron's nature is to make 3 bonds, but that's when boron's neutral. Clearly, we're not in a neutral situation here, right? Something's got a charge.
No,
I, Captain.
You can't do the eyes next to each other?
That is not the nature of iodine. Go to our discussion yesterday or Monday. We had fluorine. Nature, 3 lone pairs, 1 bond. Everything in that column, same nature. Okay. There's your skeleton.
but now we gotta put the negative over the whole, right?
I'm not a fan of that. I got asked that. I think it was the ninth section. Do we have to do this, Dr. Whitaker, was the question in the ninth section. And they say this and this, and I say no. Stop. No, when it is mandatory for every formal charge that is not 0 in my class to be labeled. That will take care of the minus. And I don't need to know the overall minus because I'm going to look at this molecule. There's one formal charge showing it's a minus charge. The ion has a minus charge, right?
So how do we do that formal charge?
Formal charge, group 3 on the periodic table means 0 formal charge. If this boron owns 3 electrons, owns, O-W-N, it owns half of 8 because there's 4 bonds. What's half of 8? It's 4. I just like counting the bonds. That's easier, right? You get your 4 that way. 1, 2, 3, 4. Boron owns 4 here. It owns 1 on the 3 on the periodic table. Sorry. It owns 4 here. It owns 3 on the periodic. It owns 1 more electron here. Then over there, it has a -1 formal charge here. -1. You put it like that. I prefer to circle it because it's a formal charge. You don't have to circle it, but I like it. And part A is almost over. We've got 8 electrons on this structure so far with the 4 bonds. How many more do I have to put on? 24. I like to put them on the outside until the octets are full, which is perfect because 3 times 4 is 3 times 8. Sorry. Well, 4 times 6 is 24. Where was I going with that? I don't know. I got 3 lone pairs for each iodine gives me 6 electrons, right? And then the times 4 is going to finish off 24. 2, 4, 6. 2, 4, 6. I'm sorry, that first one was a little messy. I don't care, as long as I count 6. And that is final answer for A. I'm going to write it as final answer for A. I need to see that on your quiz or activity or whatever you want to call it. We're going to continue for BCD. Okay. Redraw the structure with proper geometry. Okay, so the Lewis part's really over. I'm going to redraw it, and I'm going to have to explain myself when I'm done. Okay. In terms of geometry, you want me to do just a quick review of, I don't know, is it just 5 geometries in this class or 6? I'm not even sure. Let's go over them. Geometries are all based on hybridization. Did you know that? And hybridization is a representation of the number of sigma bonds added to the number of lone pairs. So what 2 things do you count to determine hybridization? You count sigma bonds. Remember, that's the first bond between any 2 atoms. There's only 1 sigma bond between any 2 atoms. Only 1, and it's the first bond. Okay? So you count that, and you count lone pairs on the same atom. And when you get the number 4, the hybridization is called sp3. When you get the number 3, the hybridization is called sp2. When you get the number 2, the hybridization is called sp. Okay? All right. S and p are types of orbitals, aren't they? We can't use atomic orbitals to make bonds because the angles would be irregular. We want evenly spaced things, right? There's that thing called Vesper that's vaguely in your memory, right? And it's a beautiful theory. The name is actually the theory. Valence shell electron pairs repel each other. That means they want to be as far apart from each other as possible. Yes. Okay. And we're talking about sigma bonds and lone pairs. Those are the things you can spread around. You can't spread around a pi bond. You know why? Because if there's a sigma bond in an atom between, and there's 2 bonds between 2 atoms, one of them's a sigma. We know that, right? What's the other bond? Pi. And once you put the sigma there, the pi has to be on each side of it, either that way or that way. It can't be sticking off in a different direction. I mean, these atoms are there and there. They have to be, the bonds all have to be between them. So the only 2 things you count, remind me, for doing hybridization? Sigma bonds, lone pairs, boron. How many sigma bonds? 4. How many fingers? Because there's no lone pairs. I'm not adding any more. Boron does not have any lone pairs here. Fact. You're only putting up 4 fingers. Fact. What's the hybridization for 4? You forgot? S, P, P, P. Put the P's together, please. sp3. Now, review 141. What's the bond angle for sp3? 109.5. We only have 3 bond angles to memorize in this course for the 3 hybridizations.
SP3 was the trigonal.
Ah, that's next, but it's not going to be trigonal.
No.
Yeah, that's when there's a lone pair. 4 sigma bonds, tetrahedral. Now the question is, how do you draw a tetrahedral? Well, 2 of the bonds are in the plane of the page, 109.5 from each other. In fact, we want it to be a nice Lewis structure, right? We got 1 really short bond there. I want them to be the same length. Well, the other 2 bonds are not in the same plane. Okay? One of them is sticking out of the page, equidistant between these 2. So one of them is sticking out of the page, and one is sticking behind the page, right behind that. And it's a geometry question now. I'm not worried about lone pairs. You don't have to do those. You did those when you did the Lewis structure. And please put the formal charge on. And that is B. That's a tetrahedron. You'll see videos on properly drawing tetrahedra. There are. And there's the illegal tetrahedra and legal. Just remember, the wedge and dash both have to be away from the bonds that weren't wedges and dashes. What did he just say? Here's a wedge. Here's a dash. Here's a bond that's not a wedge, and there's the angle to the other bond without a wedge. I need the wedge and dash between these on the opposite side. Do not put them in here. That's bad geometry. You can have some angles real small and some angles real big. No, we want even angles. What number again for the angles, please?
109.
Every one of them, 109.5 because of the hybridization. 4 sigma bonds. That's not 4 degrees. No. 4 sigma bonds plus 0 LP lone pairs equals 4 equals sp3. Got it? And we got more angles, you know? I think there's even another one. I don't know, I can't label it really. The angle between the iodine up here and down here, 109.5. Hard to show. You could write the sentence, all angles 109.5 right there, and you're done. How about we do that? Watch. Get rid of all that work because it's too much work. You can give me the same knowledge. Oh gosh, I didn't want to get rid of that. That was useful. I'm going to get rid of this. I'm going to point to boron and say all angles off of the boron, 109.5. And its name. What was the name of this geometry? Tetrahedral. And what was the angle? I believe that is how I want answer C. No, B. No, I didn't even ask for it. You need it. That's okay. It's right there.
What are the dipole vectors?
Oh, I'm glad you asked. All right, dipole vectors are a measure of polarity. A big vector means there's a large difference in electronegativity. It means the charge is separated between the atoms. I'll just demonstrate quickly right here. I got atom A and atom B, and they have the same electronegativity. That means the electrons are, on average, exactly halfway between the atoms because they have the same electronegativity. Here's atom A and atom B. Atom A has a higher electronegativity now. That means the electrons are closer to A than they are B. There's a dipole. This is a slightly negative ion. The A ion is, atom. It's not an ion. It's a covalent bond, right? They're not ions. So A, if it's more electronegative than B, will be a slightly negative atom. And the B, conversely, is slightly positive. That creates a dipole vector that points towards the more electronegative atom. And I will show that on the page right now.
Over here, they go towards the B.
No, B is 2.1.
Oh.
Have we learned our electronegativities? We're going to, please, this weekend. Yes, I is 2.5. Yes, please, have to. It's like not knowing the definition of the word "the" before you read a book. That's how fundamental electronegativities are.
Well, we have the periodic table.
You have the periodic table, you do not have any electronegativities on it. But yes, that's good for trends, isn't it? Yeah. And on this page, we also have F coming up. And H, correct? On the next molecule. Oh, B is not 2.0. 1, sorry, it's 2.0. Yeah, there's, hey, videos you're going to see memory tricks. The textbook has the same memory tricks. It's not like 30 numbers. It's like a group of 4 here, a group of 2 here, and with memory tricks to connect them. Okay? There's so much help for this. Please don't just use these videos and say, oh, he only wants us to know these 4. No, there's a table that says these are electronegativities you must know in the biggest font size in the whole chapter. Okay? And there we are, electronegativity. That means we have a dipole vector between the B and the F. And I'm going to draw it like this. Yeah, it doesn't quite point the right direction. It needs to point exactly along the bond. That's pretty close. And why does it point that direction? Because F is more electronegative. And what is the difference between those? Delta En for the red one is 4 minus 2.5, right? 2.0 equals 2.0. That's a big difference, by the way. That's a delta. That's a mass symbol this time. I'm just botching it up. Ah, my computer's harsh. This one will look like a triangle. Yeah. There you go. What about B and I? What's the difference? No, it's not 2.0.
I am more electronegative.
Yeah, and the difference is only what, 0.5, which is a quarter of 2.0. Yeah. So for my, we'll go with black vectors. A quarter the length of that arrow that I just drew is the length of the black arrow. Why? Because the difference in electronegativity is a quarter. Delta En for all of these bonds, 2.5 minus 2.0. That's a quarter of 2. So I'm going to draw a vector that's a quarter the length of this one. I know it's in the wrong direction, but that's what computers are for. I don't know what the heck happened there. You see that? That was trippy. You know how you check if it's a quarter? You don't have to do this on your test. That's 2. I think it's a little short. Right? A little short. There's 4 of them. It's short. Heck. 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 What about there? What do you think? That's about a quarter. And I'm always going to point them towards the iodines, right? Well, I know it's not pointing towards an iodine now. That's why we have computers. I'm going to group it. I'm going to rotate it. Oh, look at that. That's not fair. There, right along that bond, right? Now this one goes right along this bond. Well, there's the head, there's the tail. The tail is always where the less electronegative atom is, right? Please think of the tail as a plus sign. Think about it. You're the atom that's less electronegative. Aren't you the plus one? Yeah, the plus is near the plus atom. There's a plus near the plus boron for the red. And what about this? This one points along this bond. All the black ones are really the same length. Okay. So that's all part B. Okay, what are dipole vectors are C. So we got B and C going on at the same time. And now we're supposed to add those together. Oh boy. Oh. You want to do it proper addition of vectors? Proper addition of vectors is easy. They're addable, you know. There's a vector. Well, more than a vector apparently. Copy the vector somewhere on your page where that vector ends, which is the head, start and end, is where you begin the next vector. You pick one of the other 3. If I'm lucky, I'll get this one. No, I didn't get any. I'm not lucky. I don't even know what I'm grabbing. There. I'll get just I got the whole deal. Where that one ends, start this one. Where that one ends, I don't know what I'm going to get there. I got most of it. Start this one. And where I don't have this this one yet, the wedge, right? Anyway, that one didn't see that. And because I'm a terrible artist, it didn't work out like it should.
Well, it's too bad.
You know, it should have ended right on the red line, but I'm a bad artist.
And then those are the Dipole vectors?
No, the net result is supposed to be from, you know, guys, here, I'm going to tell you what me being a bad artist means. Okay. Here's the length of my arm here is a vector, right? And when it's sticking out of the page, what's the length of the arm that you see? You see it's a lot shorter. You're only seeing this. It should, I mean, when the third dimension's added, it kind of shrinks one of the things just based on the way you're looking at it. That means these were oversized, right? Because one's going behind the page, but you only see like that distance. But I drew it the same distance. I'm just a bad artist. And the good news is I don't make you do this on the test. So they just stop listening now. But you know what I'm trying to say is I'm going to get the red guy. It's probably best to move. Maybe down. Just want this. I just want this. And I said they were a little too big. Just based on trying to draw things in a three-dimensional thing in 2 dimensions. And it really should end up on that red now. That's a lot better. And I'm going to tell you how to get past that right now. The net is from the very start. That was the first vector I drew. And the last one I drew was here, very end. Net is from the very start to the very end only. That's the molecular polarity. This represents the molecular polarity. So that's a pretty polar molecule. As drawn, the dipole vector is pointing straight to the left. And here's how you would do the three-dimensional problem and make it simple. I just want to illustrate wedge dash to you, and here we go. I got 2 wedges, right? Right? So I'm going to add this one, and then I'm going to draw the other one over here and there. It ended up straight in front of me. You see that? There, and this one I moved over to here, and it ended straight in front of me. So what's the average of wedging, you know, these 2 wedges? Exactly the middle. Twist it a little bit. I got wedge dash. Now it's this way. Wedge dash. Pretend the board is my body. All right? And what's halfway between the wedge and the dash? I'm looking straight ahead, right? Yeah, so this one goes out and comes back when I copy this over here. It's there. So that's how you get rid of the wedge dash. Do the average of those, not the average, the sum of those 2, right? So here, what's the middle of the wedge dash? Right in the middle on the page, right? There's no more wedge dash because the middle of a wedge and a dash is the page. And it's going to look exactly like this, but the mirror image because it's down here, right? Please think about that. When you add these 2, you get this. Wedge plus dash equals exactly in the middle there. And then I'm going to take this thing and add it there. Plus x, call this x, is this plus x. Do you see they're going right along the page? And now you're adding the FB bond, that's the big red one, to this little one. And it's just subtracting a little bit from the red one, isn't it? Because it's opposite direction. And you end up with this. This little red one is just this now, coming back. You can, when you're adding numbers, can't you add the first and last number and then the middle two and then get the total after that? Or couldn't you add one number here and then the total of these three added to that is the same as the total of the four? It doesn't matter how you do the math, right? You break it down into smaller things. Well, vectors are the same, except they have direction involved as well. And we got our net dipole, and you're still confused because it's brand new. There's lots of videos on this. Please watch them. Okay. And I think we're going to make this a double activity because it took a lot of time. And so activity 3 is going to be 2 points. And you don't have to trade pages.